Welcome to solverfy.
In this case, we have a beam, and let me just throw a little schematic of that here. We have this beam here, we have a mass, a block on it that has some force acting on it, and then there's a damper down below here, and these ends are pinned. So we have, again, because of this, the beam acts as our spring, and then we have this damper down here that will dissipate mechanical energy. And then I think we have, it's running an eccentric flywheel, so we have a rotating unbalance for our amplitude of our forcing. We're told that the motor weighs 200 pounds, and the static deflection of this beam, when you put the motor on it, is 2 inches. We're told that the weight of the unbalance on the whatever you call it, the eccentric flywheel is 1 pound, and it acts at a distance of 5 inches from the axis of rotation. We can figure out the spring constant by dividing the weight by the static deflection, so we get 1,200 pounds per foot. We're told that the motor is spinning at 100 RPM, so we need to convert that to radians per second, and that gives us 10.47 radians per second. And one thing to note here is when you're converting from RPM to radians per second, it's basically a factor of 10, because 2 pi is pretty close to 6. So you're basically dividing by something close to a factor of 10. So you should always see that the radians per second should be about a factor of 10 lower than the revolutions per minute. And we need to get this in radians per second to use it in our formula for the amplitude of the excitation. So that's the weight or the mass of the eccentric flywheel times the distance from the rotation axis times that rotation speed squared, and that winds up being 1.42 pounds. We are, let's see here, we're told actually the damping ratio is 0.2 or 20%. The natural frequency we can then find using getting the mass out of the weight here and using our stiffness, and that turns out to be 13.9 radians per second. Now, the amplitude of the response, again, we can just look this up from the book, is F dot over K, so this is the static deflection here. And then we have this denominator again, that's 1 minus r squared plus 2 zeta r all squared, and then the square root of that whole thing. We can figure out what r is because we know the forcing frequency and we know the natural frequency, and they're pretty close to one another, so r is going to be fairly close to 1. And we know this value, we know this value, we know r, we know zeta, and so we can just plug everything into here. And we get that what we get out is 0.00224 feet, or 0.0269 inches. So we don't have a whole lot of excitation response here, and because that's a lot of the reason because this is a very small amplitude of the load that's acting on the beam. Even though we're getting close to resonance, we still have a very small load, and actually quite a bit of damping too.